So the earthquake of 24th August 2016 in central Italy killed almost 300 people and left homeless more than 5,000. A walk down the main street of Amatrice, which is what you're seeing, is the best way to grasp the extent of destruction that this earthquake produced. As we walk down the main corso, we can see that some buildings are completely collapsed, while others remain standing, even though they were seriously damaged. In a strong event like this, as engineers, we expect that the buildings will be damaged, but will remain standing. We call this life safety performance. In other end, we expect that people will be able to walk away from the building with their lives. Doing this it's possible for a new building. We know how to do it pretty well. It's more difficult to strengthen or retrofit existing building to actually perform in the same way. And we have to say many of the buildings in Amatrice that you see on the ground have been retrofitted to a certain extent. So the question is why this intervention didn't work. In the rest of my talk, what I hope to share with you is some evidence from past earthquakes of how far back the problem goes and what type of measures have been taken historically and also more recently. What is the typical recovery process, we'll see, and where we need specific knowledge and resources in order to ensure that the process takes place and it concludes positively. We will then look at what are the Italian code provision to strengthen historic buildings, and I will show you some simple examples from past earthquake and also more recent attempt at strengthening buildings, including some of the research that we are carrying out at UCL, and we will get onto some conclusions. If we look at our past, we can identify in the 20th century a number of earthquakes which had a devastating effect on the Italian territory, populations and economy. As you can see from this photo and from the figures, although the magnitudes are not as strong as earthquakes in the Pacific, in Japan, or in the USA, in California, the effect has just been as devastating, if not more. I don't know how many in the audience have knowledge of these events, but it's certainly, I mean, as far as I'm concerned, it is after the earthquake in 1980. As a teenager, I went there as a voluntary that I decided to become an earthquake engineer. Coming to things more closer to our days, many of you will remember the collapse of the vault of the Basilica in Assisi, the deaths of several children in a school that recently retrofitted in San Giuliano di Puglia, the death of several university students in L'Aquila, in a reinforced concrete building that hosted a dormitory, the deaths of workers in reinforced concrete prefabricated factory buildings in Emilia, and finally the events in Amatrice that saw the death of many tourists that had gathered there for a pasta festival to celebrate the famous Amatriciana recipe. The question is always why this happened and what are we doing to avoid this in future, and what have we done and why are we not prepared. And the question is legitimate because when we look at maps of Italy, this map shows what we call a shape map, the epicenter of the 2016 earthquake. In red, the area that we call of the main shaping, so where we expect more damage. and then in yellow areas where the earthquake was felt, and we know that it was felt as far as Rome, Perugia, and further afield even in Firenze. But we can imagine that this is a relatively circumscribed event and relatively isolated. However, again, if we take this slightly longer historical perspective, 40 years, you can then see there are 5 major, not so destructive events, but 5 events over the space of about 40 years, from 1979 in Norcia, and then in Gubbio in 1984, in Colfiorito in 1997, then Gualdotadino the following years, then more recently L'Aquila, and finally the series of events of Amatrice, which I'm showing here the 26th of August, but indeed then that was also followed by other 2 earthquakes towards the end of October and 1 more in January. So you can see that not only the epicenter are very closely aligned, those clouds of point represent the aftershocks, but also the aftershocks are very closely aligned, and altogether they very clearly identify the fault system of the Sibylline Mountains and the Monti della Laga, which actually cause historically all these earthquakes in this area. So, knowing that there was an earthquake in Norcia in 1975, 9 for instance, should have alerted population and people and authority to the fact that there could have been an earthquake later on, north of it or south of it, and so on. And hence, did we prepare our buildings to withstand those earthquakes? But let's leave for a moment the end of the 20th century and let's go back in time. Again, this is not new. We have records for Norcia or for L'Aquila that date back to the 1300s. And indeed, we have record of these also in paintings of the 13th century, 14th century, and 15th century, which shows very clearly and pictorially exactly the same things that we see today. So again, it's 500 years that this happened. Our building stock is as old as these paintings in some cases. Why? Very often when I speak to people from the United States or from other countries, they ask, why do you keep living in these buildings? You know that they are going to kill you. Why do you keep living in these buildings? And the only answer that we can give to a certain extent is, well, because they are part of our heritage and they are part of our culture, and they represent with their environment the way in which some of us, or many of us in Italy, but also in other parts of Europe, like to live. And that's the main reason why we keep living there. But it is true that maybe we should try to do something about it. And indeed, we have done something about it as engineers. The awareness of the seismicity of the overall Italian territory and the need to build better housing was first voiced publicly and nationally by Pirro Ligorio, which we all know in the 17th century. Later on, after the earthquake in 1786 in Calabria, Italian engineers came about with what is referred to as Casa Baraccata, a system built in timber, which was supposed to be an answer post this very destructive earthquake in 1786 to reconstruct Calabria. Some people say that Calabria, the so-called Mezzogiorno problem in Italy, can be dated back to that particular event. However, in modern engineering terms, the concept of earthquake engineering and building to withstand earthquakes has not really met the scientific standards until 1906, after the Messina earthquake in Italy, but also contemporary in San Francisco with an earthquake in the same years, and or similarly in Tokyo with an earthquake in 1903. So globally, the community came to the recognition that something has to be done. This slide shows how the, let's say, how the awareness of the pericolosità sismica, the seismicity of the country has developed in these 100 years, since 1909. And initially we had only 2 seismic zones, then we actually instituted in 1976 what was called the Seismic National Service. Finally, in 1984 we produced the first seismic map, which had 3 zones, and in this one, Amatrice was, which is this area here, was in zone 2. There was then an update of the maps after the 1997 earthquake, and you can see that some areas have become more dangerous around here. This is the L'Aquila region, but some areas have indeed become less dangerous. If you look to Sicily, for instance. And
Dina, why the Tuscania was a big earthquake in the 70s?
No, this is not bigger. This is how seismic it was meant to be. And there have been an earthquake near Lucca, in the Lucca area, so at that time it was considered highly seismic. And then this has been reduced in seismicity. Now we have slightly different, a more refined approach. So let's say the recognition that a territory is seismic prone is the first step towards introducing something. So the maps were introduced in the 70s, most of the building stock was already there. So what are we going to do about a building stock that has already been built, has not been built to seismic standard, and needs retrofitting if people are going to live there? And indeed, the problem becomes all the more stringent when we looked at built heritage. What do we mean by built heritage? For the UNESCO definition, built heritage or architectural heritage is anything that has cultural significance. And cultural significance means that it's either has aesthetic significance, historic, scientific, social, spiritual, has any value for the past, the present, or the future generation. Cultural significance is embodied in the place itself, in its fabric, where we intend the materials and the way that they are laid out, the setting, the use, the associations, meanings, records, anything that is related to the place and related to these objects that we look at. This is the definition that ICOMOS produced in UNESCO. So, in ICOMOS terms, cultural significance, heritage significance, and cultural heritage are synonymous. And hence, any building that has more than 100 years, it's by definition, because it's of interest for a past generation, a present generation, and a future generation that is still standing, has some cultural significance. From the point of view of how do we identify that cultural significance, the keywords, let's say, is authenticity. So it has to be authentic. It has really to be what it was, and it continues to be. And from an engineering point of view, as you can see, the authenticity can be embodied in various elements, but from an engineering point of view, what we are interested in is the design, the materials, and the workmanship. That's what embodied what we call structural authenticity or structural, and at the same time, structural integrity. And why these two concepts are so important and they should go together? Because the structural integrity allows the building to stand up and be reliable and be safe. And the structural authenticity provides, through the structure, the meaning of and the value of that, the heritage value of that particular asset, object, in this case, a church in a matrician. So, what happens then is that we need to be very careful when we implement a strengthening procedure, because on one hand we want the authenticity to be preserved, so we shouldn't put there anything that is new or that falsify the way in which the building works, the building reacts. But at the same time, we need to preserve the life of the people that actually occupy the building. And hence, we need to intervene to improve a fabric and a structures that we know very well is deficient, because this has been proven over and over. So, I'm here just listing some of the criteria that we try as conservation engineers to adhere to, among which the fact that the strengthening should be compatible with the original material, should be durable so that it lasts and we can rely on it. Very importantly, should be reversible. If in 10 years' time, through technological development, I find out that something works better, I should be able to undo what I've done before and improve it. It should be monitorable. When I intervene, I should have a meaning to understand how much I've improved that behavior. Think of all of these like hip replacement. Yes? If the hip doesn't work anymore, you go to the surgeon and you ask for a hip replacement. And they're going to remove the head of your femoral bone, and they're going to do something which is made of a different material, which is synthetic. They are going to connect it in a way that doesn't have anything to do with the way that your bone has grown in time. But if it's well done, it might last 20 years and it might allow you to deambulate and go around London fairly comfortably. Now, this is exactly the same concept. What is it that we need to add, remove, add, substitute in such a way that the buildings will behave better? And how do we make sure? So, this is in, let's say, it's what we try to adhere to. In practice, I just want to show you here very briefly what does it mean an earthquake for a building or a number of buildings, and how do we go back to what it were. So at time zero, here we have the time, the building is damaged, so it loses its integrity and its capacity to withstand load. The day after the earthquake, we start with something that we call tagging. Here we go around and we say this building should be demolished, this building should be, cannot be entered, this building is still safe and can be used. We then start with debris clearance, and if the building is like it's an historic and valuable building, we should also start a process of documentation and storage. How many carved stone there are in this pile of rubble, that we would like to be able to reinstate once the building is repaired. What artifacts were in the church that needs to be quickly removed and put to storage so that they are not going to be perished. After this, once this is done, we should be able to shore and make safe, which is something that in this earthquake didn't happen so much, while it was extensively implemented after the L'Aquila earthquake, for instance. And there has been a lot of debates in the news and elsewhere of why this didn't happen. And we also need to demolish things that are not safe and that can fall on people's heads. After this, that usually takes place in the first few weeks after the earthquake, then on the assumption that we are in a position to rebuild or repair or restore that building, then we need to start our phase of understanding. We need to study why the building failed. We need to document it, monitor it, analyze it, and really come to terms with what is doable. And this takes some time because, of course, in most cases, there are no ready plans, yes, for such an event. So the documentation, we don't know where it is, the archives are never updated, and so on. And very often, when you go into the archives, you find out new things. We then need to decide whether it is feasible that the building goes back to its prior use, because it's a building at risk, has been damaged, and for whatever we can do to repair it, it might be that it's not able to function as before. Yes? So if you have your rig replaced, maybe you will not run the meters as you were using earlier. On the basis of this decision, we can start coming up with a preliminary design. At that point, this phase can usually take some months if it started immediately. After these few months, let's say 6 to 8 to 10 months, then let's say that we have a preliminary design, we need to find the money. It's as simple as that. And assuming that the funding process, either through governmental funding, which hence has an either that depends on the political system, then we can then start developing what we call a detailed design, so start thinking specifically of what it is that we will do. And as you can see here, things can be done so that the building slowly is going back to its original state. Possibly we start here in a space of 1 year, maybe we go on site and we actually build it up, and then slowly again the building is, maybe we will need to change things from the detailed design because again we find out new things while we are on site. And this process altogether might take up to 5 years. Indeed, soon after the earthquake in Amatrice, there were some studies done in the Emilia region because it was just about 4 years after the earthquake there. And they are, in many cases, especially for historic buildings, they are still in this phase. In the case of L'Aquila, we all know that 7 years, no, 8 years have passed now, and possibly we are still in this phase for many buildings, and for some we are still in this phase. So, although I've given a time perspective, this is not always responded to. So, what are we doing when we talk about preliminary and detailed design? What is it that engineers can come up with that can make buildings work better? Now, like with everything else, the technology moves on with time, and we find out, for instance, that when you have an hip replacement, well, the metal head was a good solution in the 80s because stainless steel was supposed to be the best things possible. Later on, they substituted that with titanium. Then they found that titanium was very heavy and it produced a lot of problems for the muscles. You were not quite able to lift your legs anymore. And so now they have replaced this instead with FRP and fiber reinforced plastic, which are as light as bones, and possibly, we don't know whether they will wear out quicker than titanium, but if they were, they will replace you the hip again, possibly. And similarly, in earthquake engineering, in the 70s, all our knowledge was based on reinforced concrete. And there was very little understanding of the relationship between our reinforced concrete work and our masonry works. And as we were able to design nice reinforced concrete frames that withstand earthquakes, we all thought that, yes, well, let's put as much reinforced concrete in a masonry building, and if we stiffen it enough and we give it a certain, what we call a box behavior, it's bound to work well. And so away we went with what we call a ring beam, nice roofed plate made of concrete slabs, with any walls that was made of stones and mortar. We sort of shotcreted or covered it in encased in concrete, in the understanding that the concrete will do the work where the masonry was not capable of doing it. Other type of intervention, and these strengthening strategies were recommended in the ministerial decree of 1986. So after the 1997 earthquake, there was clear understanding, and there was plenty of evidence that actually this type of strengthening didn't work well. For instance, the collapse of the vault in the Assisi Basilica indeed was due to the presence of a very stiff ring beam with roof slab, which caused the failure. Things that in the meantime we found out that might work better is to actually inject the masonry with what we call mortar grout, which works better in connecting the stones there, but still relies on the stones and the mortar to do the job rather than external concrete. And also, we realized with some work done also by my group and others, that ties, which were only used since the 18th century, are actually a very good use and a very good tool to make the building behave. If we needed, as I said, there was already evidence in the earthquake in 1997 that ring beams didn't work, and in fact in the L'Aquila earthquake in 2009 we had confirmation of this, because basically all the churches that were damaged in the L'Aquila earthquake are in the main Duomo, the main cathedral. You can see the ring beam here, and you can see what that caused. This is the Colle Maggiore Basilica, where you can see the ring beam hanging from its reinforcement out of the at the top of the arches, and there is a big gaping hole similar to this one. And this is the Santa Maria Paganica church, where again we have exactly the same type of damage and the same type of reinforcement. All of these roofs were substituted between the 60s and the 70s in the genuine beliefs that it would improve their behavior. Again, further confirmation of this we had in Norcia This is what is called the Contro Cattedrale, because it's built just in front of the main cathedral of San Benedetto, which collapsed. And here we have, you can see here that there are buttresses in this wall, which were inserted in the 18th century, after the earthquake in 1703. This wall is still standing, and the campanile, which is all tied up with anchors, is still standing. The facade, which are behind here, are reinforced concrete and steel structures that was supporting the roof, was actually damaged in the earthquake of October. There are also some other more technical reasons why the damage occurred, but this is not so important. This is a building in Arquata, which, as you can see, is in very poor condition at our visit 2 months after the earthquake. This building is very interesting because virtually every single reinforcement and strengthening device that the engineer thought of through the time had been included in this building. At this level we have reinforced concrete slabs. Then up here in front we have some anchors that didn't seem to work well. Then later on here you might see some joists that are coming down. And if I change picture and we look at the other side of the building, you can see the joist hanging here. So this was basically a very modern type of reinforced floor. And here you can see these are the space for the roof beams, and this is a concrete ring beam which has come down 4 stories, so about 15 meters, and it's like 600 millimeters deep, so it's something like that, made of concrete, which is very heavy, on top of masonry, which, as you can see, is made basically of very round stone and mortar. So the surprise is that it stayed there for 30 years, not that it came down. And the first shaking, unfortunately. But of course, it's very easy to make jokes with insight. And so one needs to be very careful. More recently, after the earthquake in 2009 and with the research work that we have done in the last 30 years, we have identified all a number of things that work and don't work. So we have, for instance, identified a way of obtaining the same effect of the concrete ring beam without putting a concrete ring beam, simply by improving the way in which the top of the building is built in masonry. For instance, using FRP, reinforced fiber reinforced polymer strips. However, when we went on a visit 2 years or 3 years ago in L'Aquila, when we were looking at some historic buildings that were restored, so we look at building being grouted, and this seems to work well. We went, but although the code recommendation says that this type of intervention is not recommended, there is no proof that it works. It's extensively done because it's very cheap, quick, and it takes, and you don't need as skilled labor as to put instead some brickwork here to reinforce the walls. And we still, people still coat their masonry in concrete, although again there is plenty of evidence that this doesn't really work well. So again, there is a matter also of how we educate and will improve the understanding of the profession at large in order to improve the behavior. This is, for instance, again an intervention in L'Aquila using a very recent technology, which is again the use of FRP with basically drilling through the thickness of the wall and then inserting FRP bars and then post-tensioning them. The idea is that this should be more, you can see here where each of these stains on these walls is actually an FRP bar that has gone through and that has been, this is a close-up of it so that you can see how it works. There is no evidence that this actually is going to work. There is no evidence. Nobody has tested properly and so on. However, in L'Aquila, almost all the buildings have undergone some of this work, just because the contractors know how to do it. Somebody, the supplier sells the FRP, and this is what is being approved. And of course, when you look at this is a building of the 18th century. Think about the authenticity and think about the maintenance of the historic value of this building. There are things done properly, so this is Palazzo Ardinghelli still in L'Aquila, and here they have gone back, my colleagues, they have gone back to the idea of the ties and the anchors, the traditional anchors, and they have simply used them in a more systematic way in order to obtain a systematic response. And this is the finished product, and you can see they are quite unobtrusive. You see very little of them. From an architectonic point of view, they don't disturb the facade. It's not too bad. And next to it, you can see a building that had traditional ties in L'Aquila, which was not damaged. However, even though this is a much better example than the previous one, we know, again, through events in the previous 30 years, so here we are going back again to 1997, that the traditional anchors as implemented in this case might and might not be, they might be effective if we look at life safety. As you can see, this building is still standing, so people have been able to evacuate safely, to come away with their life. However, the building is seriously damaged to a certain extent, irreparably, and hence it will need to be either newly restored or very seriously altered. So it's with this in mind that recent work that we are doing, work that we have started since 2010 when I was at the University of Bath, that we are now bringing forward at UCL. We work on what we call a dissipating device. This is a friction device that we can put in series with traditional anchors, and simply when the earthquakes, when a force is exerted more than a certain amount, it will start sliding and in this way start dissipating. This object has been already patented, and in order to make sure that it is a feasible pursuit, we actually have the possibility of putting it in situ in a building that had been damaged in L'Aquila, in the oratory of San Giuseppe dei Mini, and you can see here there is a clear, very clear crack that separated the main facade from the rest of the building. So we inserted our anchors, which is this one. So this is the front of the anchors that goes on the facade. This is our device here, and this is the back of the anchors that goes in the side walls. We inserted it here. and we instrumented the anchor so as to be able to see whether it's effective when there are tremors. And indeed, we managed to pick up some tremors during the year in which it was kept in place. And we can see that the dissipative element is responding more than the other elements, and it's actually dissipating more energy than the other parts. We can, of course, this is one particular case that proves things up to a certain point, but we are in a position to actually simulate the behavior of these objects with numerical analysis and also with laboratory testing, and hence determine the behavior and arrive at the situation in which we can design each of these interventions on a building by building specific and manufacture them in such a way that they are specific to the buildings. This really concludes my presentation. So just to say that the earthquake engineering community indeed has shown an increased sensitivity towards the importance of preservation and historic buildings, and promotes research into the assessment of new assessment of strengthening methods. This is reflected in the code provision, although we are not quite there, and as I said earlier, the real issue is how to train and how to update the ability of people on the ground. It's good that in the academic circles we do these things, but it has to get to the single building. Very important is a very critical issue is how the interventions are implemented and the quality control that there is behind the contractor. And of course, when you have a large number of buildings that you need to retrofit or you need to repair, it's very difficult to control that each and every single one of them is done properly. So, and I don't know whether in Italy a control system exists and is effective on the ground. It exists, of course, on paper, whether it is effective on the ground, but this is also a problem not just of Italy, but any other country in the world. And I think we are proving, and that's why we are now investing more efforts and money in further developing these devices, that they can actually be a new and more efficient way of preventing damage in historic buildings. Thank you very much.
Thank you very much, Dina. Very clear, impeccable timing. So, questions?
Hi, my name is Roberto Medaglia. I saw in the last slide,
yes,
probably was a finite element simulation or something like this, the thing here.
Yes.
Now the question is, to which extent one can use simulations, which I think you use extensively, to evaluate the opportunity of using certain solutions instead of other solutions. Clearly this is not easy because you have to put in all the details of the building and the details of the structure, which is the beams, the concrete beams, or whatever. So it's a complicated thing. But this could be, if you come up with a picture like this, which tells you which is good and which is bad. You could do the same with any other solutions and convince whoever has to make it work that their solution is viable or not. So the simulation, I think, takes into account the shaking of the earthquake. So, are you using? It's possible to use simulations to convince people that one solution is better than another one?
Yes, to an extent. Of course, simulations. Well, we don't really call these simulations.
Yeah.
we call this numerical analysis, which is a slightly different things than a simulation. It depends, of course, these are models, and like when you model something, you are abstracting from reality and you are reducing reality to something that you can actually deal with your tools. So of course you are by default, eliminating some issues. You are simplifying. Nonetheless, the numerical tools that we can use nowadays are quite sophisticated, and as long as we have sufficient documentation and information to put as correct as possible numbers in, then we will have responses that are credible and realistic. So when I initially mentioned the period of study, documentation, collection of information and so on, which can take some months, this is exactly to produce for any specific building that you want to intervene on, the set of data and the set of information that is good enough to warrant going on to do a study of that type. These simulations, this is a relatively simple model that we are showing here, but really they can become quite complex and they can take quite a length of time to produce results. So it's worth investing in something like that once you have good enough information to put in. You're welcome.
Thank you. I don't know anything of the subject, so just a really simple question. I guess there's two ways in which the soil itself, the nature where the earthquake is taking place, can affect A, how a building is affected, and B, how it's reconstructed. So I always thought the more flexibility a building had, the better in it not falling down. On the other hand, if you have a very movable soil, like near a coast, you would imagine the whole thing can collapse more easily. When it comes to building, how do you take the soil into account in terms of, I guess, achieving that optimum flexibility without the risk of it being very difficult?
Yes, well, this is a very pertinent question, and it's very difficult to answer in a few words because it requires, let's say, course, a program of in earthquake engineering, but as some of the people here have gone through. But nonetheless, I'll try to explain it as clearly as I can in a few words. The earthquake is a vibration, and like all vibrations, it's like sound. Yes, in the sound you have different harmonics and you have different frequencies. The earthquake also has different harmonics and different frequencies. Now, what causes damage is the fact that the content in frequency that is close to the natural frequency, what we call natural frequency of the building, is what will amplify that response and hence eventually be very damaging. However, that in itself is not a problem as long as the building might be subjected to the very high load, i.e. a very high amplification, but if like amplifier, you have a membrane that is strong enough that can take the full volume, It will vibrate a lot, it will deform a lot, but then when you put down the volume, it's back where it were. Now, the problem with masonry buildings is that they don't have that capacity of vibrate because they don't have that tensile strength. So as even relatively modest earthquakes, if as soon as the building goes a little bit out of kilt, out of vertical, it will start cracking, and once it starts cracking, it will start coming apart. So it's in the case of masonry building, it's not so much about how flexible they are, because they are not very flexible, but it's more about how that tensile integrity can be kept, and that's why we put mortar into the core, and we not rigid. We just try to improve their strength, their capacity to take tension. So that's one aspect. As far as the soil is concerned, the problem is that when the earthquake comes from the ground and it's filtered through the soil. So again, as I said earlier, depending on whether the soil is very compact, i.e. it's a rock, or it's very loose, i.e. sand, you mentioned near a coast, but not necessarily near a coast, then the way in which we'll amplify certain components will be more or less high. For instance, if we have very solid rock, it will probably amplify, it will have typically one main component, so it will amplify just one component of the earthquake. And if the building is this side or the other side of that component, it will not experience a very high amplification. But in loose soil, although the amplification is not very high, the number of frequencies that can be amplified is much larger, and hence it might impact on more type of building, on more type of structures. Also, if the soil is very loose, it will behave in the same way as a masonry structure, i.e. at the first wave, it will start coming apart. And then if you have what we call superficial foundation, then it will fall away. And that's where the soil is important. That's where in large buildings we do deep pile foundations in order to avoid the superficial stage. Yeah.
Let me ask a question, which is really naive. So Italy has had earthquakes, as you illustrated, for hundreds of years.
We have records that go back to the Romans.
That's right.
In fact, before the Romans.
Right. And still today, we have very damaging earthquakes. People that lose their lives. Now, if today you had enough money to fix all the buildings, which, well, first of all, has somebody evaluated how much money is necessary to fix all the buildings in the seismic area of Italy, which is essentially all Italy. Because otherwise, next time an earthquake comes, no one has done anything, but yes. How much money is necessary?
Okay,
And the second question, once the money problem is solved, the second question is there a consensus on how? Is there a consensus in the scientific community on what should be done? Because from what you say, I have the impression that not everybody thinks the same way. So if somebody has enough money to fix the entire central part of Italy where there is all this serious problem of possible future earthquakes, there would be a consensus on what to do.
Okay, again, two very interesting questions. I think that the National Association of Engineers had made a rapid calculation after the earthquake in Amatrice and come up with a figure of something like 89, I don't know why not 90, but 89 billion pounds, billions euro, billion, 89 billion euros, which is a considerable amount of money. However,
This is for entire,
this is for the retrofitting of all the buildings that we think they have not been designed according to the code. But there might be buildings that we think that have been designed according to the code, which are not. So, or which are not being built according to the code. So, I think in order to resolve the economic problem, there are two ways. One is to think about how each earthquake is costing in terms of reconstruction. And when we think about the reconstruction, it's not just the money that goes into rebuilding the building, but it's also the loss of business, the loss of life, the loss of culture, the loss of everything. Yes? And the fact that, for instance, in a place like L'Aquila, basically you have a city that is completely dead, or partially dead. So this is one thing. The other thing that we need to think about it is that in Italy, like in many other parts of Europe, most of the buildings are being, or will be, or are being retrofitted to comply with the energy policies, because we have decided that we need to spend less money in heating or cooling them, and they need to be better insulated, and and people are spending this money to improve their buildings because there are governmental incentives, because they will pay smaller electricity bill, there will be less CO2 emission. So why don't we apply the same set of thinking or the same mindset to the issue of retrofitting building to withstand earthquake? Of course, it's not as easy to implement, but it's more disruptive to everyday life, perhaps for a certain time, but on the other hand, we can save a life. So I think until that mental shift doesn't take place, but not just in the government, it has to take place in the public, because money for retrofitting, as I said, after the 1997 earthquake and after Amatrice was reclassified, they received money to retrofit their building. Now, some did, some didn't, some did, and the building came down anyway. But almost all the cases that I've seen, the retrofitting and the 60 centimeters concrete ring beam that I've shown you were so that you could actually gain some space under the roof and to all extent have another floor to rent. So, you know, okay, it's an investment, but you are playing with your life. So are you ready to do this? Or so I think it's until the recent widespread safety culture, it's very difficult to implement a proper program of retrofitting. In terms of the community, I think that, as I said, at academic level, I think that there is substantial agreement of what works and what doesn't. So there is mostly agreement about what doesn't work. There are commercial and market pressures. So, for instance, the chemical giants, multinationals, they produce the FRP fibers. Of course, they want to sell it, and hence they invest a lot of money in. They first have produced it for the aeronautical industry. That is more or less saturated because you cannot produce more aeroplane than a certain amount per year. So, okay, let's use it as a strengthening. Then they have tried to put it in cars, then now they are trying to put it in buildings. In fact, for the last 20 years they are trying to put it in buildings. It's clearly a market, and it might be that it works well, and it might be that it doesn't work so well. You know, it very much depends on, say, individual, the way in which it's used, and maybe there's yet not sufficient evidence to prove that it always works well.
All right. Yes.
Well, thank you. Very interesting talk.
That gentleman was waiting to ask.
Usual.
Yes.
I was just going to ask a very practical question, and that is that the buildings insurance industry must be a very complicated one in this seismic area. So do the building insurance premiums correlate to whether or not a building has...
Building insurance for earthquake purposes exists to a certain extent in California, mainly for business, a little less for residential building, but for a certain extent, yes. It exists in New Zealand, and more or less in the same way, and in Japan. In the rest of the world, it's a myth. In the sense that, for instance, in Italy, the government pays when a building is damaged by an earthquake. So while we have fire and flood, or we have premiums against fires and floods for buildings, there is no premium for earthquake. And they are now trying to introduce it. But basically, when an event like this occurs, the government pays, then there is a raise in some of the tax that relate to the built environment, and that's how the government replenishes its coffers. Please.
Yes. Are vaulted ceilings, are they better than flat ceilings? How do they withstand earthquakes better? Or can't you generalize from that? Because I'm not thinking of, obviously, the obvious ones are churches. I'm thinking actually farmhouses in Sicily often have ground floors which are, well, for cellars, which are vaulted.
Yes.
And the upper floors are flat ceilings. And other buildings do the same. Is it done for earthquake reasons, or to prevent the damage from earthquakes?
Okay. So, in fact, this is a very acute observation, because what we have seen both in L'Aquila and in Amatrice is that 3 to 4 stories building, many have collapsed, but the ground floor, which was vaulted, is still standing. And this is because typically that first floor, vaulted first floor, it's built in such a way with very large walls that this vaulted ceilings or vaulted structure has not very much what we call thrust, so it doesn't tend to, or better, it pushes, but the wall is capable of taking that push. Typically, as you go further up with floors, and also buildings at ground floor very often are built one against the other, and so they are very stable. As you go up in stories, in some architectures, you will also have vaulted structures at a higher level, although they tend to be thinner. For instance, in L'Aquila, you would have it at first, second, third story, but they will tend to be very thin, cross vaults and so on. And in churches, if they are not properly buttresses and propped, then they become liability.
So are you saying that the ground floors withstand it better simply because the walls are much thicker, not because of the vault?
No, not necessarily because of it.
I always thought that the forces will distribute better if you have a pointed arch, for instance.
Yes, to a certain extent, yes.
But not.
Well, a flat floor costs much less to build. You just put some timber and some planks, and it doesn't necessarily warm worse if you put anchors, if you tie it with the walls.
Can I ask you another question, which was related to the question that Roberto asked you at the
Yes.
beginning? So, you made the analogy between hip replacement and...
Yes.
So, but if I have a hip replacement, I hope I won't have a hip replacement, but if I do get a hip replacement, and then I do an X-ray and see whether the hip has been put properly.
Yes.
Now, what can you do to see whether works to
Yes.
fix buildings are done properly? Do you have proper instruments?
So that's there are we are in this field we are really borrowing from the medical technology and the medical science, and we are indeed trying to use X-ray, but they don't work very well in masonry. Or better, they don't penetrate very well. So for instance, if you are looking at timber and you're looking for nails or steel connectors in timbers, X-ray is a good thing, but if in masonry it's not so good. We use something that's called ground penetrating radar, so this is our ultrasonic pulses, which penetrates better in solid mass like masonry. Again, it's not as, and they allow you to identify voids. We also use sonic or ultrasonic wave, and now we have methodology and technology that allow us to do what we call 3D tomography, which is a little bit like TAC. Yes, and again, that allows you, if it's very well done, allows you to see, for instance, if within a wall there are different density. So when we do the grouting, then we can do some ultrasonic testing in order to see whether the grouting has actually penetrated sufficiently into the core of the wall and as compartment, the voids are being eliminated. So there are some of these techniques. They are still relatively expensive. In a diagnostic terms, we use something that we have been using for quite a while, and it's very, quite reliable, which I haven't shown anything, but it's called flat jacks. So you imagine the jack of a car, yes? You put some oil or pump it up and it goes up. So this is flat, it's like this, with some oils in it. You cut the mortar and you fit it into the mortar joint, and then you start pumping, and that gives you a very good idea of how strong the masonry is and how it holds together, what are its characteristics. So there are ways of let's say, what we say monitoring and testing, and we call it non-destructive testing, although in some cases a bit destructive.
Right, last question.
Sorry for the others. My question, because it's the last one, may I raise two questions, but very quick. So, the second to last is, why the ring beam doesn't perform well?
Why the ring beam doesn't perform well?
Because for what I've been told, that they are the key in allowing the natural structure to work as a 3D structure,
yes,
to distribute forces, to connect the slab with the wall. So I've been taught in that way. But
yes,
maybe my professors were.
Well, yes, this was, as I said, the knowledge that we had in the 90s. So why don't they work?
Just
yes,
the quick one is about the technology FRP.
Yes.
I would assume if the technology has been tested and
yes,
proper procedure, European technical approval has been
yeah,
done, I would expect that should be fine to adopt those technologies. So either those procedures haven't been followed properly, or they've been followed, but okay, the random 5% of possibilities that there was anyway a problem, whichever was the problem. Or what do you reckon is the problem with FRP or
No. In the case of FRP, there are, as I said, there are some work that is done. For instance, it's applied quite extensively on reinforced concrete structures. And in the last 20 years, a large amount of testing has been carried out and a lot of trial and errors, design and so on, to actually arrive at very rigorous guidelines on how they can be used. And these guidelines have European approval, have US approval in the US and so on, and they are now used worldwide. Now, the fact that it works with reinforced concrete structures, i.e. it works with beam and columns, doesn't mean that it works as well with arable stone walls. And there hasn't been the same level of testing, investigation and proving that there has been for the concrete framing. So I'm not saying that they don't work, I'm just saying that we should be cautious. Also, one thing that is not properly resolved is the long-term response of these materials, because we don't really know what has happened. And we also need to think that when we typically retrofit a concrete structures, we think of a life expectancy of that structures of about 50 years, and maybe total 50 years, maybe we retrofit it after 20 or 25 years, and so we predict that we assume that in the next 10 to 20 years it will be demolished for other reasons. When we look at these historic buildings, they have already been there for 100 years. They are of cultural value, they are of heritage value. We expect that they will be there for another 100 or 200 years. So we need to be particularly cautious about what we use and how, and what is the life expectancy of the strengthening approach that we take. So that for the FRP. The previous question about the ring beam, again, it needs sort of, I need pen and paper or drawing boards, but again, I will try to explain it in simple terms. What happens is that, yes, basically what we are trying to achieve is what we call the box behavior. Yes? So if you take a shoes box, yes, and you take the lid out and you push the sides of the box, you will see that they tend to come in. Once you put the lid on top, they become much more rigid. So that's the concept of the ring beam. And the ring beam as a concept is indeed what we want to achieve. The issue is why the concrete ring beam doesn't work. And the reason why they don't work on this type of structure is because it's a lot of mass that you put there, and it increases the mass of the structure instead of reducing it, which is not, and it's all at the top. And your oscillation and your amplification will become greater. Typically, the beam will take a lot of what we call shear, so a lot of the force, but then that force needs to be transferred to the wall, and the wall has a very modest shear resistance. So what we typically saw a lot in the earthquake in the Umbria Marche is that because these buildings were not very tall, all the roofs are moved 25 centimeters away from the wall, yes? They all think that done that. What we call shear. It's like if you cut your cake and then you push it a bit. Yes?
It looks like that both for the ring beam and the applied technology, the problem is not in the technology of the concept itself, is the extrapolation going too far to the application of that idea, the original idea to wrong application.
Yeah. Yes, that's always something that we should be very mindful of.
Thank you.
You're welcome.
Right, so thank you very much, Dina, for a very